Hello everyone, we are here to share our understanding on flow through porous media. Throughout this presentation, we'll be discussing about the basics of pore-scale modeling, the different experimental reconstruction methods, and the different continuum and pore-scale models. And also we are going to talk about the pore-scale modeling done in solid oxide fuel cells and also the challenges faced in pore-scale and in pore-scale modeling in general. So what is a pore? A porous medium is defined as the solid matrix which is interconnected by pores. These pores can be either filled with fluid or they can be voids as well. And based on the structure of the pores, they can be defined as passing pores, non-passing pores, and isolated pores. And based on the structure of the pores, the porous media can be characterized from the specific surface area, porosity, and partition coefficient. So there are the practical applications of porous media ubiquitous. They find their applications in heat exchangers, fuel cells, batteries, packed bed reactors, biological systems, and so on. So it is important for us to effectively model pore scale to understand how the porous media affects the transport properties and the various physiochemical properties to gain the better understanding of why these systems are much more efficient. So in order to do that, there are basically two approaches. One such approach is a pore-scale modeling approach, and the other is a continuum scale modeling approach. In the pore-scale modeling approach, we are focusing only on the individual pores rather than the whole porous media. And this is done at the microscopic levels from 1 micrometer to 10 nanometers range. So in the continuum scale modeling approach, the porous medium is considered as a continuous media where the pore properties such as porosity, fluid velocity, and also permeability are averaged in the form of taking a representative elementary volume. So what is this representative elementary volume? Representative elementary volume is taken as the bridge between the continuum scale and the pore scale model, and it is used to define parameters such as permeability and porosity of the porous media. So representative elementary volume is defined as the smallest volume, which effectively represents the whole porous media in general. So one such main condition imposed in the REV is that the measured properties such as the permeability and porosity of the porous media generally remain relatively constant along the REV. So in order to experimentally determine the porous media to effectively develop the pore-scale models, we are using 3D scanning techniques such as focused ion beam SEM, X-ray computational tomography, and also other analysis like transmission electron microscopy to develop efficient porous structure to actually model efficient porous structures. So how is this done? We are going to take an example of modeling of pore-scale models of platinum on carbon electrode. So using the FIB SEM and the nano CT, we are able to effectively model the porous pore scale in greater detail, but it lacks much more important things such as the individual constituents present in the porous media such as platinum and the carbon. So in order to do that, further analysis by TEMP actually provides us the constituents and their geometry. And this is effectively done to recreate the porous media for better understanding of the phenomena occurring in that scale. So moving on to the continuum scale models, and one of the most important equation that we use to model porous media is the Darcy's equation, which provides the relationship between fluid velocity and the pressure with inclusion of certain pore parameters such as hydraulic permeability. And to incorporate viscous effects of fluid flow in porous media, the extension of Darcy's equation called Darcy's Brinkman equation is used by using a viscous coupling term, which incorporates the viscous effects of fluid flow into it. So this law is only valid under highly porous media, and the other form of the Darcy's equation is the Darcy-Forchheimer equation, which includes the inertial effects of fluid flow. This equation is applicable only at very high velocities where Darcy's law is invalid. So you can see that by removing all the Brinkman term and the Forchheimer term, you essentially rewrite the Darcy's law. So these are the one such common flaw in these models is that it does not capture the heterogeneity of the pore scale effectively, which could be an issue if you are going to look at very small phenomena like in electrodes and in fuel cells. So in order to effectively capture such heterogeneities, different pore scale models are used. So one such model is the lattice Boltzmann model. So lattice Boltzmann model uses tracks the probability distribution function of the particle and sees how it changes with time, momentum, and position. So, in essence, it could be said that the Boltzmann equation effectively balances out the changes in particle distribution due to free particle motion, external forces acting on the particles, and also the collision between the particles. So, you can see that effectively this term represents the free motion of the particle. This term represents the forces acting on the particle, and this is the collisions between the particles. So this equation is solved into its discrete form, and it is solved furtherly, which could be explained in the later part of the presentation. Moving on.
Hi everyone, I am Sagar. So I am going to talk about the post-scale modeling. So which kind of equations we are using? So this is a general equation that we've already studied. If we replace the unknown terms such as rho star phi or lambda phi, so we can convert this equation into mass conversion, momentum conversion, energy conversion, concentration conversion. Okay, next. So this is the Boltzmann equation, that latest Boltzmann method that we are going to use to solve the post-scale model, that can be used in the different phenomena such as electrodes used in positive electron membrane exchange or the batteries. So this represent in this method, what they say is that motion of fluid is represented as a particle distribution function, and that is defined as Fi. So Fixt is the density distribution, and along with it, Fi equilibrium, Fi-eq is equal to equilibrium density and such other parameters as well. Okay, next. So now to solve this method, there are different approaches that we can use. One is single relaxation time, and one there is multiple relaxation time approach. We are going to discuss on multiple relaxation time approach or MRT approach because it gives a better result for permeability. Now permeability is independent of fluid that is being discussed. So in the single relaxation time, that is a limitation that it depends on the viscosity of the fluid that is being examined. But whereas in MRT approach, it is independent of that, and that is we want to focus on. Now to solve the above equation, same approaches that we have done in the class, that we are going to use different kind of boundary conditions. Now here there are 4 boundary conditions, but for the sake of presentation, we are going to limit ourselves to only 2. First one I will be discussing as a no slip boundary condition, which is represented in this figure. So I will just explain the figure. So gray area is represented as a solid part. The white and blue area is represented as different fluid such as gas or liquid. The orange area is represented as a transition area through which the gases or fluid, it will transit from fluid to solid part. Now, the A point is represented as a no slip condition. The B part is represented as a heat transfer boundary condition. So we'll start with the no slip condition first. Okay, next. So as discussed in the class, so this is the equation that is used for no slip boundary condition. So I is the direction of solid to fluid and I cap is the inverse direction. Now for the second boundary condition, where there is a heat transfer that we are discussing at the solid fluid interface. So for that sake of understanding, what we are saying is that temperature is same at the boundary condition for fluid and solid, and flux as well, heat flux. So now to solve this equation, what we are going to do is we are going to use the energy conversion equation, and we are going to apply it over to fluid side and the solid side. While we are applying to fluid side, we know that for the steady state, for the heat transfer, we are going to discuss ourselves limit to only steady state part. So uh, du by dt term will goes to 0 because it is a steady state term. And for the fluid, the first equation will be that del ut equal to del lambda f by rho cpf del t, and the second equation is 0 equal to lambda del s by rho cp s delta t. That is for solid because solid is at rest and we are taking fluid at some velocity. Now if we use the regular method like we did it in the Navier-Stokes equation, we need to do interpolation or extrapolation. But in this method, we can directly solve with the below boundary condition. Okay, next. Now we are going to discuss one of the macroscopic property that we discussed for the pore scale modeling in the class as well, that is permeability. Now for the permeability over here in this topic, we are going to take three different scenarios. One, we are going to start with fibrous porous media. Now for the fibrous porous media, the permeability is represented by equation K by R square equal to 5.5 divided by this first equation. Now for that, the porosity is in the range of 0.4 to 0.95. Then another porous media that we are going to discuss is random fibrous porous media. For that, the second equation is going to be used, and the values of that is also represented in that. There is only one difference, is that epsilon c is involved in this equation, that is a threshold porosity. Okay, next. Okay, so this is the as discussed, the A figure represents the fibrous part, B represents the random fibrous part, and the figure C represents the layered fibrous pores, that is equivalent to, let's say, in the battery or electrodes that are used in positive exchange membranes. So for the figure C, the equation shown is also used for the same. So this is the macroscopic property, and we can now move forward for applications of these equations or the model.
Hi everyone, my name is Neha Bollineni. I'm going to explain about the applications in different porous media. Porous media has a lot of applications in geoscience, proton exchange fuel cell, polymer exchange membrane fuel cells, and solid oxide fuel cells. I'll go with one of the application of porous media in solid oxide fuel cell. These are the fuel cells operating at very high temperature, typically from 8,000 to 1000 degrees Celsius. They are called solid oxide because their electrolyte is made up of solid ceramic material. This has mainly three components: anode, electrode, uh, cathode, electrolyte. Anode elec- is called negative electrode. The function of it facilitates the oxygen of fuel, whereas the electrolyte function is to conduct oxygen ions, that is O2 minus, from the cathode to the anode while being impermeable to the gases. It only allows ionic conduction, whereas the cathode function is to reduce oxygen from air to form oxygen ions. So now we can see in figure, the oxygen ions are coming from cathode and passing through electrode to the anode. The electrolyte here is dense structure, whereas the anode and cathode are pore structures. The pore media play a crucial role in the operation and performance of SOFCs, particularly in the anode, cathode, and sometimes in intermediate layers. Here is a detailed breakdown of their functions. Moving forward, the transport processes in fuel and oxygen delivery, both the anode and cathode need to facilitate the movement of gases. So the anode needs fuel while the cathode requires oxygen from the air. So the porous structure allows these gases to diffuse uniformly across the electrode surfaces, ensuring that the entire active area participates in the electrochemical reactions. Going to how it is affecting the reaction zone is the triple phase boundary, that is TPB, where the gas, electrode material, and electrolyte meet each other, is the site of electrochemical reaction. Porous maximizes the TPB by enabling gases access deep into the electrode material, enhancing reaction efficiency. Now, going forward to enhanced electrochemical reaction rates, the effect of porous medium and catalytic activity is in the anode, the porous structure supports catalytic activity, helping fuel molecules to react effectively with the oxide ions. How porous media is affecting surface area is it increases the surface area, as we can see in figure 7. Enhanced electrochemical reaction rates in SOFCs depends on improving the active surface area, particularly through porous electrode structures. These porous materials provide a large interface for gas diffusion and electrochemical reaction, particularly at TPBs, that is triple point boundaries, where the fuel, electrode, and electrolyte meet each other. For example, in figure, a composite of LSCF with porous increased oxygen vacancy ions accelerating the oxygen reducing reaction, that is called ORR, by providing more active catalytic sites. Now going to thermal management. So the porous media is affecting the heat distribution. The SOFCs operate at very high temperature, as we know, from 800 degrees to 1000 degrees Celsius. And porous electrodes help in distributing heat eventually across the cell. This prevents electrolyte overheating and minimizing thermal stresses and also improving the durability of the cell. And it is also affecting insulation and expansion. The porous structures of SOFCs allows for slight thermal expansion of materials without including significant mechanical stresses. As the cell heats up, typically from 800 to 1000 degrees Celsius, the ability to accommodate thermal expansion prevents cracks or material failures. This flexibility is crucial for maintaining the long-term stability and performance of the cell. By reducing the thermal stresses, the porous structure enhances the durability and reliability of SOFCs during the operation. In figure 8, we can see the image shows a CFD simulation of temperature distribution within the fuel cell. The highlighting where the highest and lowest temperatures are, we can see. This helps in understanding thermal behavior, ensuring efficient performance, and preventing damage due to the overheating. Now we'll move forward to the challenges faced by porous media.
Hi everyone, my name is Dharav, and I'll be going over what are the challenges and why, and even their potential solutions maybe. And I'll be strictly going over the challenges which are mentioned in a research paper which we have referred to, which is pore-scale modeling of complex transport phenomena in porous media. So first is computational challenges. So pore-scale modeling, it requires like large numerical grids in order to resolve the geometry of the porous media accurately. um, and the cost of the computing cost, like the computing cost, increases drastically with increasing resolution. Like if we need more resolution, we need more computing power, which results in more cost. So what are the kind of methods to reduce the computational load? So I'll be talking over two methods. First is using machine learning, and second is using multi-scale decomposition. So first is machine learning integration. So right now, like machine learning techniques are for this thing, it's kind of used to predict the transport properties. So how do we do that? So firstly, we generate a training data set. The data set, and then that data set is kind of feed into the system. So the model trains itself by reading that data set. And then we apply like three different models which are talked. So firstly, support vector regressor, Gaussian process regressor, and then convolutional neural networks. These are the three models which kind of would suit this application. And then so first is using machine learning, and second is using multi-scale decomposition. So in this method, let's take an example of physical variable like velocity. So a physical variable like velocity is kind of split into two parts: volume average and then local deviation. So what is volume average? Volume average is it kind of captures the global variation with long wavelengths, while local deviation, the second part, it captures like the smaller fluctuations. So then how is it solved using multi-scale decomposition? We use the method of tridiagonal matrix algorithm. It is also called as TDMA. That is used to solve it. Going forward, second challenge is 3D recognition techniques and the challenges. So 3D recognition techniques, they are often used, but then they have like limited resolution. Like they have resolution limits that they can only go up to certain limit. Like I'll be talking about one of them, which is FIBSEM, which stands for focused ion beam scanning electron microscopy. So it can only achieve resolution like up to 2 nanometers. Like it cannot go beyond that. So what are the potential solutions which could help in this matter? So the two solutions which have been discussed. The first is atom probe tomography. It's APT, and the second is neural network techniques. So first of all, what is atom probe topography? It's a kind of relatively new technique. Um, and it's kind of capable of 3D recognition at a sub-nanometer scale. So it can go beyond 2 nanometer, which is our limitation right now. But then this APT technical has also its own limitations. Like since it's relatively new, like it can only be applied to certain materials and certain use cases. Second is neural network techniques. So it's similar to the one which I talked about earlier, which is machine learning. So deep learning or deep learning models can kind of learn the patterns in low resolution, and then it can predict the finer details to generate the high resolution data. So if you don't have a high resolution thing, it's fine. Like we can feed in the data to the system which is of low resolution, and then it can like predict on its own what would be the final details, which is kind of really cool. But then it also has its own limitations. For the flow in porous media, like neural network techniques have not been like extensively applied, so it's not really common to see them in here. Going forward, topology optimization and its limitations. So first of all, what is topology optimization? Topology optimization, it's a mathematical approach which is used to design structures by optimizing their shape and material distribution. So we optimize the shape and material distribution, and it's under like certain constraints and all. On the figure, we can see like we optimized like we go from left to right, and the rightmost is the one which is optimized figure. So in port scale modeling, it is used to optimize polar structures to enhance the transport properties. So what are the current applications? So currently, topology optimization is used in designing of heat exchangers. It's also used in designing of uh, optimizing porous electrodes in batteries. Um, and then, but it also has its own limitations. So it assumes 2D in steady state process, but then in real world it's not 2D, and it's also not steady state. And again, the other limitation is it requires a high memory and computation requirements. So what can be done in future for this? It needs to be kind of applied to 3D and also unsteady state, since the real systems are like that. And also like multiple processes can be made at the same time. So let's say heat transfer and mass transfer are going at the same time. Those kinds of models need to be developed. Yeah, going forward. So this is our references. This is all we have referred to. Yeah, that's it from our side. Thank you very much. We can stop.